ever stop and think about how your computer actually does anything? How does a game save your progress, or how does your browser put these words on your screen? Well, it turns out there's a secret language, a fundamental process that lets our programs talk to the computer's core to get anything important done. And today, we're going to pull back that curtain and demystify the system call. So to get this, you first have to picture a massive, invisible wall running right down the middle of your computer. And no, this isn't a bug, it's actually one of the most important features. It's there for protection, to keep the whole system safe if one single program decides to go rogue. See, this wall splits your computer's brain into two totally different zones. On one side, you've got user space. Think of it like a sandbox or a playground where all your apps, your browser, your text editor get to run. They can play, but they have very limited power. On the other side of the wall is the high-security kernel space. This is the computer's control center, the absolute core of the operating system, with total command over everything. Okay, so that brings up a really obvious question, right? If our programs are stuck in the playground, and all the important stuff is locked away in this fortress, how does anything actually get done? How do they even talk to each other? The answer is a super-structured, super-secure communication channel. And probably the best way to picture this whole setup is to think of it like a bank. The kernel has this one, official, heavily guarded teller window that programs have to use to make requests. It's the only bridge between these two worlds. Let's run with that analogy. The kernel space, with all its power over your hardware, that's the bank vault. It's totally locked down. Your program running over in user space is just a customer out in the lobby. It can't just waltz into the vault and grab what it needs. No way. It has to go through the proper channels. And that official channel, that proper procedure, that is what we call a system call. It is the one and only approved way for a program in the lobby to ask the kernel in the vault to do something for it. Whether that's opening a file, writing to the screen, or making a network connection. So how does a program actually make one of these requests? It's not like it can just yell at the teller. There's this very specific 4-step procedure it has to follow every single time. And it goes a little something like this. First, the program has to pick what it wants from a menu. It does this by putting a specific service number into a little box on the CPU called the EAX register. Second, it has to fill out all the necessary forms, these are the arguments, and puts them in other little boxes like EBX and ECX. Third, and this is the important part, it rings the bell for service. This is a special instruction, interrupt 0x80, that basically forces the kernel to pay attention. And finally, step 4, after the job is done, the kernel hands back a receipt, the result of the operation, in that same EAX box where it all started. Now, I know that sounds pretty abstract, so let's make it real. We're going to watch a program go through those exact 4 steps to ask the kernel to do something super simple, write a short message to your screen. Alright, here's our blank request form. These are the CPU registers, those boxes we were just talking about. Before our program can ask for anything, it has to fill this out perfectly. Okay, step 1, choose the service. Our program wants to write something. Well, the official service number for the write system call, or syswrite, is to number 4. So boom, it puts a 4 right into the EAX register. The kernel's going to see that number and know exactly what's being asked. Step 2 is filling out the rest of the paperwork. The syswrite service needs 3 more pieces of info. First, where are we writing? The number 1 in EBX means standard output, which is just a fancy way of saying your screen. Second, what are we writing? The location of the message, MSK, goes into ECX. And third, how long is it? It's 4 characters long, so a 4 goes into EDX. And just like that, our form is filled out. And now for the big one. Step 3. The program runs the instruction int 0x80. This is it. This is the bell on the teller's counter. This instruction literally stops the whole system, switches context from the program's playground into the kernel's secure control center, and forces the kernel to look at the request we so carefully prepared. So the kernel takes over. It looks at the service number, 4. It reads the arguments. Write to the screen, use this message, it's this long, and it does the job. Safely. Then, it immediately hands control right back to our program in user space, like nothing ever happened. The transaction is complete. But how does our program know it worked? Well, the kernel gives it that receipt we talked about. It puts a result code, like a success or failure number, right back into the EAX register. It's the perfect way to close the loop and let the program know if the write was successful. Now, here's what's so incredible about all this. That little four-step dance we just saw, it isn't just for writing text to a screen. It is the fundamental mechanism that powers almost every single meaningful thing your computer does. Writing to the screen is just one item on the kernel's huge service menu. There's sysopen for opening a file, sysread to get data from it, sysexit to close your program down. Each one has its own unique number that goes in EAX, but they all follow that same secure four-step process. So you might be thinking, why all the fuss? Well, it boils down to three massive advantages. First, security. That wall we talked about, it means one buggy app can't burn down the whole house. It can't crash your operating system. Second, it makes things so much simpler for developers. They don't need to know the intimate details of every hard drive model. They just ask the kernel to write a file and the kernel figures it out. And third, it's the foundation of everything. Saving a file, opening a web page, printing a document, it's all built on system calls. So the next time you click save or just see a letter appear as you type, you'll know what's really going on. Your app is politely filling out a form, ringing a little bell, and asking the kernel to do the heavy lifting. It really makes you wonder what other secret languages and hidden procedures are running right now just beneath the surface of your screen.